Buenos dias. Good morning, Bill.
Good morning.
Good morning, Bill.
Yeah.
I guess everything's all right.
Everything seems to be fine on this side. Yes.
Can you hear me all right?
Yes, your audio is good. Yeah.
Okay, that's good because I'm at a different computer today.
Ah, okay. Oh, seems to be working just fine.
Oh, that's good. Yeah, seems like the internet's pretty good today.
Mm.
How have you been up there? Cold?
Not too bad. No, we've actually had above normal temperatures. Um, it's been a pleasant long fall this year. So every once in a while we do actually have green green grass before Christmas, or even during Christmas. Every once in a while. This might be the year again for because it's
Well,
the cold
they
weather's
talk
been
about
holding off for a long time.
climate change. It's going up, melting all the ice in the Arctic.
Yes, yes, they are. Although there are some cold temperatures, not very far north of us. It's been well below zero for weeks, so it's
Oh, okay. I guess the bears are happy then.
I don't know. But I heard someone told me this morning that there's a potential uh, hurricane out in the Atlantic. They called it the rare December hurricane. I'm not sure if it's maybe just a potential, or I'm not sure whether it's actually out there yet or not. But
Where's it going?
yeah, that's always the question, isn't it? But we'll see.
I guess Dr. Cruz is coming on.
Oh, good morning. Good morning.
Good
Good
morning.
morning.
Buenos dias.
Buenos días. How are you?
Very good. I just got back here. I'm in Puebla.
Yes, I saw it's a different background.
I hope my internet's all right. It seems like it's better than in the States, actually.
Hmm.
Yes, it does seem to be very reliable this morning.
Actually, yeah, well, that's good. That's good. We hope it stays up there. I guess it's a better location here or something. It's
Okay, that's
All
good.
right.
so.
So
Did
I
you have a
did.
time?
Sorry, go ahead.
Yeah, I was going to ask whether you had a time to look at the latest version of this preprint that I sent. I actually published it on ResearchGate.
Mhm.
I haven't had any responses yet, really.
Yes, I had a quick look through it. I well, I think it would be very good if you could sort of walk us through, the main arguments,
Okay.
more or less like you were doing last meeting, but
Yeah,
maybe
it's
we'll have a
much better
chance
than
to
the
look
other
at it
version.
again.
I had really the other version was really half baked, so to speak. And of course, I'm very interested to see how Dr. Cruz can tie it in with his graph theory of Zbyszek. And I think it can be applied now directly without any trouble to graph theory too.
I have tried to put all this together, the principal ideas about the graphics. I think that I have a couple of no slides, but a couple of paragraphs that is the synthesis of this idea. Maybe I can show to you. But I think that I need to connect my another computer, because I have this here. Then maybe if you can give me a moment, I can get. But okay.
Yeah, I'm going to try to arrange to talk to some of my colleagues at UTLA maybe later this week. Well, not many, today's Wednesday, I don't have much time, but I haven't visited the campus. I just got here yesterday night.
So you'll be there for a few weeks, or
That's right,
longer?
about 4 or 5 weeks.
Ah. Escaping the cold from South Carolina.
Well, yesterday it was pouring rain, so at least I'm escaping the rain.
Escaping the rain, yes, I guess that's more the case.
It's pretty dry here, dry and clear in Puebla. Yeah, it's always touch and go, trying to set up these computers again, making sure they'll work after they've been turned off for a period of time.
Sorry, because I lost. I don't know what I had made, and then lost the connection in the other equipment, and catch this in this computer, but then I have not hear microphone, and sorry, but now I am ready for show this to you. Okay. Okay. Can you see this now?
Yes.
Yes, that's good.
Okay. Here, I am only repeating some basic definitions of graph theory. But since here, I started to introduce the ideas that was worked before. And here we start with the definition of graph with a zero cell and one cell. Here, the idea is the concept of cells permit to us to build more complex objects of graphs. In this way, a graph is a relation between different kinds of cells. Then a direct elementary graph is only a relation between the one graph of order 1 to one graph of order 2, of order O, not. Here in the graph of order not, we have only dots or vertices. Then we can build one graph only with the vertices, and then with the relation with the A1 graph, then we build a graph of vertices and arrows. This is the first idea. And in this way, we associated G O or G note with a zero morphism and G1 with a one morphism. Then the idea is going to complex this concept, and then we can build here in a more general way. Then we can have one graph or two graphs, and so on. In general, we proposed the concept of I lost here. Here. The concept of multigraph that corresponds to an nth graph, and a multigraph or multigraph that is an mn graph. Then the idea in general is going in terms of morphism to a higher degree. Then in the first level, we have a zero morphism that this need to include the identity, because identity is can be put equivalent to the to objects. In the second level, we have one morphism, and then with these two, we have a category. a category.
Yeah, yeah, I'll have to,
Okay. Mhm, mhm. And maybe you can wait to Professor Garrett.
Sure. Yeah, no problem.
No, that's not 27, 26.
Jesus, there's a reference here to a paper. There's a question mark there. It says.
Yes, because I have not incorporated in the correct label for the bibliography. But
there are
I
two
need
references. There were two papers.
Yes, no, it's only a paper by Cruz and Osievic. And this is the paper that we work in 2004. There are first papers I have here in Mendeleev. Okay. Wait a moment, please. I need to close this. Okay. And this is the paper that and the ideas that we present here was around multigraph that here is the a question that I am including in this presentation, and this was complexed to multigraph of multigraph. That this is the idea here. Then this is the paper that I am using in the reference, and there are another that we worked before with Korczynski.
Oh yeah,
and
I remember that one.
And then here there are the basic ideas of graphics, direct graphs and.
Okay, disculpe, excuse me, I had an important telephone call I had to answer from, so, but it's over, so. I missed a little bit.
Don't worry, we have only waiting for you. And then I was saying that here I had included the basic ideas of graphs, multigraph, and multigraph of multigraph. This is important because here we can think in a multigraph like a kind of multi-category. And then we can use the language of category here, and then maybe we can generalize this algebraic concepts to the ideas of Clifford algebras. Then this is I have included only these ideas here. Maybe I have to find this draft and send to you, because here there is synthesis of these ideas.
Okay, yeah, I'm interested in what Clifford algebras you're dealing with. Also, there is a woman at MIT, a professor at MIT that has used Clifford algebra for graph theory. It's in the references to the new version of the paper, of my preprint that I sent.
Okay.
Well, the main idea I think that you presented here, Jesus, is the notion of sort of higher order graphs, like graphs that are defined as morphisms between graphs.
Yes.
In a nested way. So you have a one graph, a two graph, a three graph, and these are similar in category theory to a category, to a functor, to a natural transformation. You know, like there's the usual progression. Here it's I mean, there are some geometric analogies that you might use to describe, say, for example, a two graph. Like we think of a one graph as being a network of connections, but a two graph is something a little bit more complicated. And I think in at least one of the papers that you mentioned, I'm not sure if it was that one, or perhaps in maybe it was in some tutorial material that was prepared by Oshevich. He talked about two graphs as being like the river that connects the the boundary between Mexico and the United States, something like that. There was the idea that in a
Yes,
it's kind of like a geometric picture that you can apply to understand what these higher order graphs could represent.
Yes, yes, I can maybe make some graphics here in the other.
Well, the reason why I mentioned this, I think, is that you need some sort of intuition or geographic intuition to see how this could perhaps apply to Clifford algebra or something like this. Right? But I think the connection isn't immediate. It's
yeah. I have an immediate. Yeah, of course, I want to see how it's related to the work I'm doing as well, where I name all vertices are named by null vectors, which have square zero.
The past session at the end, I show one complete graph in terms of a hierarchical graph. Then here we have a multigraph. In fact, we have a multigraph here because you can see that the complexity of the relations in this complete graph can be analyzed in different levels of complexity. And then with the ideas of using this for Clifford algebra, I think that this can be useful for that. Then the idea is this, and following, I am going to take my pencil for writing in this document.
But would it be true that that if a Clifford algebra is associated with a one graph, then a two graph would be associated with a mapping between Clifford algebras, or the sets of mappings between sets of Clifford algebras. So if we had a whole family of Clifford algebras, we might have mappings between these Clifford algebras. And that structure, I think, would be then a two graph, right?
Yeah, I'll talk about a specific set of Clifford algebras, namely of Lorentz space with signature 1 n-1. Okay, so you have one time-like vector, and all the rest of the vectors are space-like. Those are the Clifford algebras that I use in the paper, which I'll talk about, that I sent you. I can, when we share, I can show you how that works pretty well now. I think I understand it pretty well. I'm not sure how. I would be interested to see how it ties in with this language. It should, but vertices are named by null vectors. Namely, each vertex of a graph is named by a null vector. And I can show you some simple examples when I go to my paper.
Sorry, I am trying to connect here. Okay. Because here the idea is this. Maybe I can. We are working. I am going to put only a complete graph of 3 elements. And then here we have all the possible connections between. Then the idea is that we can close these dots because they are of the same kind of objects, and then I have here a category, with different directions. And here we have a monad. The idea is that a monad can be used for define an algebra. And then when we go from this kind of object, no, excuse me, for this kind of graphics, then this define one kind of algebra. If I go to this define another kind of algebra. And the idea is that we can use this kind of language for going to higher order algebras in the same way that we can go to higher order graphics. If you can see, this can be interpreted like I am referring to this picture now. We can interpret this like a more complex relation between objects that are going to higher order graphics. And here,
so do you have an example of a single vertex? What is a Clifford algebra that represents a single vertex, or double or two vertices like you have there? Do you have a Clifford algebra that represents that?
Because you have here the different kind of morphemes that, okay, I am going to this in this case. I have all of these are objects that are generalized numbers, and then I can establish different kind of morphisms, and this can be, for example, close plus. I am going to represent here like by a dot the Clifford product, for example, and so we can build different kind of algebras in the way that we are introducing different kinds of operations that are morphemes here in the algebra, in the category, excuse me, in the category. Then this is the idea. But in fact, if we can modify this picture where we have the nodes out of one place, and then I am trying to draw this only with the 2 points, 2 vertices, and then we can go in this way. And finally, we can get this.
Now, what immediately comes to my mind, you could associate a vertex with instead of just a nilpotent, a nilpotent vector, have a nilpotent of order m. So a to the m minus 1 is not equal to 0, but a to the m is equal to 0. So basically, if I've only used null vectors to name vertices, but it's possible that maybe in your particular way of looking at it, would be better to assign a nilpotent with index m. So a to the m is equal to 0, but a to the m minus 1 is not equal to 0. That might be a simple way of representing your ideas there, or without using the category theory material. I'm not sure, of course.
But I don't know if we can consider that like a property of the operation of the product.
Well, yeah,
Yeah.
it's just an idea, but I can show you how I use nilpotent. Well, actually, in the preprint I sent you, I'm only really considering Greek solids or the Platonic solids in higher dimensions as my examples. That I make a conjecture about the how you get the Clifford algebra of a geometric solid, a Platonic solid. So
Because all the vertices there are of the same class of objects. All the vertices are the same class of
yeah, that's
objects.
true. That's true. That's true.
And then I can consider that like a monad.
Yeah, but what I am interested in going to higher dimensional spaces. So there are 5 Platonic solids in 3 dimensions, but in 2 dimensions, there are infinite number of, well, planar Platonic solids just in the plane, namely a hexagon or a pentagon or any of the others you can construct with infinite number of sides that are all the same. But in higher dimensions, it's limited by the sequence that John Baez talks about in a very beautiful referenced HTTP file that he's published. That is, I don't know if you've looked at it, but look at John Baez. You can see he gives a sequence of numbers. It goes 1, infinity, 5, 6, and then 3, 3, 3. For every higher dimension, there's only 3 Platonic solids. And as you go to infinite number of dimensions, the sequence of Platonic solids just goes to the number 3, which is interesting.
Yes. Okay. I need to see that paper, but I don't remember here the reference. I am going to look that, but we can think that all the algebras are monads. And then the problem is to build the morphemes in a way that they represent the properties in the algebra.
So a morphism is just a mapping
Mapping.
to a geometric algebra then, in some sense.
Yes, they are the mappings to the.
Now, so if you could do some simple examples like 2 and 3 vertices, and maybe even 4, that would be very helpful to stay with the lower dimensions, at least at first.
Okay.
But for the paper that you wrote, Dr. Sobczak, the direction of the arrows is significant, right?
Yeah, that's right. The edge is a directed edge. Can assign plus or minus sign with it.
And it's this corresponds to the signature of the Clifford algebra.
Yeah, that's right. In fact, the only ones I really have nailed down are these Lorentz Clifford algebras of signature 1m. So it has one time-like vector and all the rest of the space-like vectors then. It seems to be very appropriate for for this particular problem. Where you,
But in
yeah,
but
yeah,
in your paper here, you do refer to more general signatures.
yes. In fact, I give an example how you can just multiply by I the pseudoscalar of the element. You can get, for example, from 1, 2, you can get 3. You know, the Euclidean, the geometric algebra, the polyalgebra from the Clifford algebra 1, 2 with signature 1, 2 by just changing your. The important thing is that they anti-commute, and the pseudoscalar is not trivial. So you
It
can
is-
essentially go from one. There are a lot of relationships, isomorphisms between Clifford algebras, and you can classify them all in this way, actually.
So
But
these
the basic algebras are these, the so-called some people have called it mother algebras, where you have n comma n, equal number of vectors which have positive square and equal number of vectors that have negative square for the basis. That's a neutral geometric algebra. And then if you go n plus 1, then you have an example of a complex Clifford algebra. Yeah, so I do look at, yeah, those are really the basic ones, where you start with a neutral signature, and then you go to n plus 1, and that's the same thing as complexifying the algebra by going to a higher dimension.
But a higher dimension in your case implies a graph with a larger number of vertices, right?
That's right. That's right. You don't really need to go to higher dimension if you're staying in a graph in a 3-dimensional space. I think you can. Well, that's right. You have to
but I
go to
mean-
higher dimensionals. So again, I use the vertices. That really defines the dimension of the space. You take the wedge product of the null vectors, and you get the largest number for which they're linearly independent. Namely, their outer products is not equal to 0 for the large, and that's the dimension where the graph lies then, because any other, yeah.
But what Jesus is talking about is not the dimension or the number of vertices in the graph, but rather a hierarchy of orders of graphs, so that there are for
Yeah.
like
Yeah,
so for
maybe the
a
internet's
one graph,
failing. I'm not
a
sure.
one graph can have a large number of vertices, n vertices, but then a 2 graph consists of all those one graphs and transformations from one graphs into other one graphs. That and so it's like mappings between Clifford algebras, perhaps of different dimension.
Yes, sorry, I have not prepared nothing for present to you today. Then this is too much disorder. But the principal idea is first to collect the language of graph and go to multigraph and multigraph of multigraph. This is the first idea. And the second is to show these different kind of graphs in terms of category language. This is the second idea here. And then in this way, connect with the idea of algebra for looking the way that we can use this language for speaking about the different algebras, in particular Clifford algebra. This is the route that I like to show to you, but I need to prepare these ideas in a better way.
Mm. Yeah, it's the connection with Clifford algebra that is not immediately obvious to me when I see these like n graphs, like the multigraphs of multigraphs. Um, I think of at least in the context that Dr. Sopcich is talking about, he has associated a graph with the signature of a Clifford algebra. But then he doesn't, in his paper, I don't see a natural way of thinking about, two graphs, for example, except perhaps as mappings between Clifford algebras. And then
Yes.
three graphs would be mappings between mappings, or something like that. But I mean, I'm aware that Clifford algebra, the whole subject, has a lot of results that allow one to find isomorphisms between different Clifford algebras. I'm not so much aware of general notions of sort of algebra morphisms, like whether or not how much of Clifford algebra, say the category of Clifford algebras where the objects are Clifford algebras, to what extent the morphisms between these Clifford algebras more general than isomorphisms. So the general morphisms between the algebras, I suppose they must be studied, but I haven't done much research in that area. So
the idea is that we can think in one graphical connection with, between, for example, Grassmann algebra and multigraph. Because first we start with scalars, and then we can relate this with the dots, for example, or vertices in graphs. Then after we use the one form, and one form is equivalent to a one graph. After we go to two forms, and two forms are graphically equivalent to a natural transform. And so we can go to higher Grassmann algebras, and then we can connect this with multigraph. But then here there is a different way of looking the Grassmann product, that is an exterior product, because the Grassmann product go to a higher order here. If we try to apply these ideas to Clifford algebra, then we can think in vectors and multivectors in the same way. But there maybe we can have problems because mm, the different ways that we can define a process are not unique. There are not unique way of define this kind of relations. Then this is the idea that I am trying to follow in this presentation.
So bivectors then would the algebraic structure of bivectors would be related, say, to two graphs. Is that?
Two graphs, yes.
Yeah. So. So these would be bivectors that are not necessarily primitive bivectors. Like they're not bivectors that are the result of the Clifford product of two vectors in general. Right? So
because bivectors, I understand that in Clifford algebra we can introduce the Grassmann product, and then if we can understand this like in Grassmann algebra, like a exterior product here, then a bivector cannot be of the same category of a vector.
But you would want to think of bivectors as giving rise to transformations between vectors in a vector space or something like this. So the vector space and the morphisms between vector spaces is sort of like the level of a one graph, right? But then
because a vector is a process, is a transformation, a morphism. A vector is a morphism. Then if I take a vector is not only a process, because is a transformation, the process and the vertices, and the vertices, and for this is that I think that it's a higher order transformation. It is similar to natural transformation. This. And then this is a way of geometrically we think in this like a surface, for example. Then and this can connect with the idea of Professor Garrett of the higher order solids, for example. And okay, this is in general like the idea that I am trying to. I think that we lost connection with Professor.
Yes, he seems to have disappeared. I was hoping that he would be able to reconnect, but let me just check my email to see whether or not he's. No, he hasn't. He hasn't sent me any emails either. So, I'm not sure. So, unfortunately, he hasn't had a chance to discuss his paper. But we'll we can. I guess we could wait a little longer, but he may have some problem with his computer or internet.
Energy.
Yeah, although it seemed to be very good earlier. Oh, here he comes again. I see
Okay.
him reconnecting.
Okay.
And Dr. Sobchak, are you there?
I'm going to plug in my computer.
Yes, okay. Are you back?
Yeah, I had to do a complete restart. I don't know what happened. It's just internet.
Okay.
I'm using a hotspot again, so sorry. I had to
Oh, no problem.
completely to turn the computer off.
Jesus was just reviewing while you were gone. He was sort of reviewing what he hopes to do with these notes that he presented so far. But he was saying he admits that it doesn't go that far yet. But he did say at the end, just before you came back, that he's of the opinion that the notion of higher order Platonic solids are somehow connected with the notion of higher order graphs. But there's an interesting connection as well, I thought, that you mentioned about the notion that the algebra of bivectors is, for example, naturally associated with two graphs, whereas mostly you're presenting linear algebra, results from linear algebra, where the objects are vectors. But bivectors, the algebra of bivectors doesn't play a large role in your paper right now.
Well, I think you have to use. I define the order of a graph to be. You take all the vertices, you name them with these null vectors, and then you take the outer product of those null vectors, and you take the greatest number of them where the outer product is not zero. So that defines an M vector then, say. And then you can define all the other vertices in terms of linear combinations of those M vectors then. That's the way I think of the order of a graph. I think it's all right. I don't see anything wrong with that. Do you understand? So for a two graph, well, if the vertices is just one vertex, then if you wedge A, wedge B, it'll be equal to zero because it's just a point. It's just a one vector, a null vector, one null vector. But if you have distinct null vectors, then you take the outer product, you get not zero because it defines a bivector. Or you take 3 points. If you wedge all three of them, well, let's see. Yeah, if you wedge all three of them together, that won't be equal to zero either, because you're taking vectors from the origin. So 3 points, A wedge B wedge C won't be equal to zero. Now, if you take another vector and you're only in 3 dimensions, well, the graph's only in 3 dimensions, then any four vectors will be linearly dependent, so the outer product of all four vectors is 0.
But still, I think we need to make a distinction between dimension and order, so that the order of a graph is something
The order of a
different
graph
than,
is it lies. If it's in three-dimensional space, then the wedge product of any four vectors is equal to 0. Because any four vector, all the points are in the same three-dimensional space.
yes, but this is just dimension. It doesn't have anything to do with order as such, right? Because
Well, how
order is raising it to another level so that we have like a transformation between spaces, like the morphism, a linear algebra morphism between two linear algebras. That's like an edge in a graph where the nodes or the vertices are algebras. And then you build that structure higher.
so the edges are not in the Clifford algebra? The edges are
The
the
edges
difference
would be
between two of the
morphisms
vertices.
between. So at the two graph level, the vertices are no longer simple points. Right? They are graphs. So the morphisms map both edges and vertices into edges and vertices at the two graph level, right? And then at the three graph level, you build it.
So
build up
what's
the
the
structure like that.
what's the formal definition of the order of a graph?
Maybe I can show to you this here, because the formal definition of order of graph is can be wait a moment, I need to, okay. I'm going to clear this. For example, A1 graph, A0 graph is this.
That's a zero graph because it has no edges then, I guess, right?
Yes, have not edges. Yes.
So the edges define the order of a graph?
Not yet, no.
Okay. Not exact. I'm going to show to you one graph. For example, this. Okay. Something like this. For example, this is one graph.
Okay, a closed graph then, or whatever.
But not necessary. Not necessary. For example, here, and maybe with this. This is a one graph because here we have this kind of objects that are the relation of edges to vertex.
Okay, but if you look at the adjacency matrix of that graph, that has a dimension associated with it.
Okay, but you can have any dimension here, but we are speaking here about the order of the graph.
Okay.
The next is, for example, this. And a transformation to this. And here I have better a relation between this.
Okay, for example, one graph can be in the plane and the other graph can be in three-dimensional space. And how do you
Yes.
distinguish between those graphs?
Yes, yes.
So how do you distinguish then between a graph that's in a planar graph and a graph that is in three-dimensional space?
But there's no sense of space here, right? Only abstractly graphs. So your diagram, yes, perhaps gives the impression that we need the same number of vertices, for example, but this is not the case, right?
Okay, not necessary.
Yeah, but isn't it an advantage to put the vertices in a space? That's I think it's the easiest way to look at a graph is considered in a space. Of course, you can have infinite dimensional graphs too, then of course.
But the important part here is for two graphs, the morphisms are mappings between graphs, between one graphs.
Okay.
If I put in here in terms of adjacency matrix, for example, here I have zero in all the place in GO. Here I have an adjacency matrix with the values here. Different values. And here we have.
Now, of course, the interesting thing is once you put an adjacency,
Excuse me. We lost again the Professor Garrett.
I don't
know.
No. Perhaps his image is frozen.
But maybe he is taking problems with
Again, yes.
Mm-hmm. Yes, we lost again. Yeah. The idea that I was trying to build is that here now we need adjacent matrix, but of kind.
Like more like a
because
tensor.
Yes, we need values in this. This is a cube matrix. Huh?
Yeah. It's like a three tensor of some sort.
Right? A three tensor. Yes.
Yeah.
Mm-hmm.
So the adjacency matrix is no longer a matrix. It's a three tensor.
A tensor of
or at least an array of like an order 3 array.
Okay, so yeah. Yeah, yeah. Maybe by next week I can have a better internet. Maybe I'll figure out how to work this out a little bit better, so I'm not dropping out all the time.
But Dr. Sobchak, do you see this sort of distinction between the dimension and the order? Right? So the order is referring to the sort of the type of connectivity, in a sense, right? Between the complexity of the morphisms. So the
Okay, so it's,
morphisms in a two graph would no longer have representations as matrices.
oh, in a two graph.
Yes, and this is G2.
So what's a two graph? What's exactly a two graph? Okay, you have a one graph there. What's a two graph?
Well, that's what he's been drawing, right? Is a mapping between two graphs. I'm sorry,
Oh.
a mapping between two one graphs. The terminology. So we have a one graph on the left and a one graph on the right, and then a morphism, like that maps from the left to the right.
And then we can write in this way. With one graph.
Mm-hmm.
Then with one graph, we can have source and target here.
So what are these morphisms used for? What properties of graphs do you study with that idea?
Okay. In this, in GO, we have only identity. Identity. Here we have different kinds of morphisms. And here we have functors.
Yes, because these functors or these morphisms are constrained to respect the connectivity. Right? They don't violate the connectivity, but otherwise they are free. Right?
Mm-hmm.
So that the morphism doesn't connect two nodes which are not somehow connected in the source, right?
Yes. And then we can have here relation between morphisms and nodes, no? And nodes. And then we can go to higher order here. And the idea is that a complete graph maybe can be considered like a higher order graph. It depends of the numbers of nodes that we have.
See, a node is not a, what's the difference between a node and a vertex?
Yes.
A node is a vertex, right?
Yes, yes.
Same, yeah, synonym.
Okay. Yeah, okay, so yeah, well, I like to use the idea of a manifold or manifold theory to do graph theory rather than, it seems like your category theory is is an awful lot of extra baggage you're putting in graphs. And the question is it really necessary to do that? Can't you study graphs by using manifold theory rather than category theory? Maybe that's the question I'm asking.
But I would say that this idea of n-graphs is a kind of loosening of category theory, right? So category theory requires sort of composition, like
Yes.
whereas here we only have connectivity, like we still have the notion of a functor, but there are no requirements other than that the functor respects the connectivity. It doesn't have to commute, and doesn't have to be defined by a commutative diagram, for example.
Yeah, the role of category. My knowledge of category theory and the terminology is very limited. Just what you're giving me, actually.
There's another generalization of this. This is one particular type of generalization of graph theory, but which is kind of hierarchical in a way, right? And it, so it's I've seen it applied, for example, in the case of systems theory, like where you can define a group of processes that interact with each other, and another group of processes that interact with each other, and then you can go to a higher order and you can see how this interacting set of processes affects another interacting set of processes. And so you have this sort of hierarchical view of a system as like the body, like, for example, so you have cells and you have organs, and then you have animals, for example. So you're going up sort of levels of organization. So, but there's another type of generalization of graph theory in which an edge doesn't just connect two nodes or two vertices, but can connect three vertices or four vertices. So the edges are no longer just arrows, but they can be like higher dimensional things. So an arrow is a sort of like, in a sense, a one-dimensional thing, but in a hypergraph, I think the terminology is hypergraph, the edges connect more than two vertices at a time.
But that doesn't sound like it's an edge to me. If it connects a vertex, an edge is, I always thought it connected two vertices, and that's the definition of an edge.
Well, but in say in a Platonic solid in 3 dimensions, the edges of this solid connect more than two things, right?
Well, you have diagonals, of course. Diagonals cross through the interior of the graph.
Just think of a cube, for example. So
okay.
the edge of a cube is a square, but that square connects to 4 other squares.
Well, an edge just connects two vertices of the square. You have 4 edges that define the square.
No, but okay, let's call it, instead of using the word edge, call it the face, right?
Okay, so we have a face. Well, that's a 2-dimensional. That's a bivector then. A face is a bivector.
Mm-hmm.
And then the 3 vector is, you connect 4 vertices together, you get a 3. Generally, you get a tetrahedron with 4 vertices. So that's okay. So I guess there are just different ways of thinking about graphs. One way is category theory, but another way is using directly Clifford algebra to represent edges, 2 vertices, 3 vectors, a face, 4 vectors, a tetrahedron, and so on up the line. And you have the interior of the tetrahedron and the exterior. In fact, they all take place in Rn then.
But these, but I was making a distinction between two different generalizations of graph theory. So,
Okay,
so
is there any relationship between them that we can make, for example? So apparently I am approaching it in a different way than category theory, but can we tie them together is the question.
well, I don't, there's no, as far as I can see here, there's only a very remote relationship to category theory.
Well, but again, if you're saying that a square somehow doesn't define a plane or a bivector if it lies in the plane, or if you don't,
No,
if you're not
it has-
interested, you don't have to say it's in the plane, but you can say it's defined by four vertexes or nodes as you call them. And then an edge then is just, you can think about it any way you want, really, I guess.
But the concept that Jesus was talking about is a different generalization. Like it's a multi-level generalization, so that at his zero graph level, we just have points, but at the one graph level we have points connected by edges.
Okay,
And at the
that's fine.
2 graph level we have graphs. We have one graphs connected by morphisms to other one graphs, and this morphism maps both points and edges to points and edges.
Yes, and here I try to connect, for example, with the Grassmann algebra in the way of using
Phases, that's right. An n vector is a volume, a directed volume or whatever.
yes.
N volume. Well, that's what I'm doing as well. I'm doing the same thing. I'm using Grassmann algebra.
Because we can have an interpretation of the exterior product. Then the exterior product can be used like going in higher order graphics.
Yeah, exactly.
And
Okay.
in the same
I agree with this.
in the same way, one can think about Clifford algebra, because we go from reals to vectors, and from vectors to b vectors and vectors and so on. And then this is the idea. Then those are not only they are not of the same class of objects. This is the idea, because a b vector is a class of object different from a vector. And then
Would you repeat that one more time? An R vector is different than what?
a vector is a different class of object than a b vector. Bivector. A bivector.
Yeah, an R vector, that's right. It's a higher dimensional object.
Yes.
No, not R. No, just he said a vector. A vector is different than a bivector. Right?
Yes.
Or different than a trivector, different than, which are defined in Grassmann algebra. That was what Grassmann did with his exterior algebra.
Mm-hmm. Yes, because they are exterior. Exterior.
Yeah.
Yes. Mm-hmm. Yeah. And then
category theory does not use Grassmann algebra, or it uses Grossman algebra?
No, but I trying to use category theory here because it's a way of defining in the most abstract way algebra, and then you can find more properties of this algebra using this kind of language. And graphs are a natural, have one natural relation with category theory. Then, because it is important to see how we can use this language here in this problem.
Okay, well, like I say, I suggest we take as simple possible cases that we can and compare them at a deeper level, those basic properties, and see what we have, if we have anything new. Because, yeah, well, category, I like I say, I'd like to understand better what you're trying to do with the category theory, which you cannot do with more traditional methods of studying graphs, like adjacency matrices and so on. So if we can take some simple examples to distinguish between these two different ways of looking at things, I think would be very helpful to see just two or three vertices or nodes and various connections between those nodes and whatever edges.
Yes.
But keep things with only what, 3 or 4. We keep things as simple as possible, what we're talking about, because otherwise we get lost.
The only intersection I can see easily at the moment is the reference to Platonic solids, right? Is somehow both of these approaches, what Jesus is talking about in terms of higher order graphs or graphs of graphs, somehow ends up talking about the same abstraction that in the end that you're talking about, Dr. Sobczak, like we're somehow relating this to
Manifolds. Well, that's the thing. So how can you show with your category theory language that there are 5 Platonic solids in 3 dimensions, but they're an infinite number in 2 dimensions, and that there are 6 Platonic solids in 4 dimensions, and after that, there's only 3 in all higher dimensions?
It's
that's a very interesting problem, right?
It's something like in category theory we talk about categories, and then functor categories, and then natural transformations, right? And so we're building up to 3, but in category theory we don't go beyond that, or at least not very much. I mean, people like Bayes and Olszewicz they were interested in the notion of sort of generalizing sort of what comes after a natural transformation. But the original people who developed the ideas of category thought that you didn't have to go any higher, that all of mathematics and everything we wanted to say about algebras and mathematics could be said using just up to.
So you're denying that dimensions, like 4-dimensional space-time, you don't need to go to space-time, you want to do everything in 3 dimensions, or what?
No, it has nothing to do with dimension at all. It has to do with order, right? So the order has to do with sort of a hierarchy of relationships between things.
Okay, but would you prove, for example, that there are 6 Platonic solids in 4 dimensions? and after that, there's only 3, and then you hired him. How would you formulate that in category theory? Or how could you prove that in category theory?
No, but
Are you-
I think that the approach is not in this way, because okay, this is a particular problem that with dimensions we can find different kind of platonic solids, but both problems are the same in category theory because they are not dependent of the dimensions, but this depends of the how you define the class of objects that you are using.
Okay, but you still want to approach such problems. Okay, you're not in. How can you say then derive the same idea without using, just category theory? You have that sequence of what? 1, infinity, 5, 6, 3, 3, 3 represents what does that represent in a graph then? If you're not using if you're not
Okay, I think we are lost in connection again.
Lost the connection. Well, perhaps if Dr. If he can return to us one more time, we could agree to. Oh yeah, he is. Okay. I was going to make a suggestion that perhaps we could continue in 2 weeks' time with
Yeah.
like
okay, I guess I'm back. It's
you're
awful.
back.
I'll try to fix that next time. I'll try to get to the system. It's a little different than the system I was using before.
I'm not sure if we could continue, of course, like this, but I think we need to go to your presentation, Dr. Subject. Either we could do that now, or perhaps we could wait till next week or the week after.
Well, we could maybe try it again next week. Maybe next week I'll have a better connection.
Okay. Mhm.
Is next week possible for you, Jesus?
Yes, for me it's okay. It's okay. Yes.
Yes.
Okay,
And
let's do that then. In the meantime,
Mhm.
I'll do some. I have some other things I have to do as well. Uh, So, but let's schedule it for next week. Then what at 10 o'clock?
okay.
Well, the same time.
The same time, yes.
Same.
In 2 weeks' time, I think it would be very close to Christmas.
Yeah.
So it might be a busy time for people. So if we in 1 week we meet, then we could perhaps schedule to meet 2 weeks after that or something like that.
Okay, that's fine.
Mhm. Okay.
So have a
But
good
I
week.
think we've identified at least a potential, I think, for finding a common language, but I think there's still some uncertainty here about how or if these ideas intersect. I'm still not sure about it myself.
No. Okay. I am trying to organize these ideas that I have been presented today and try to send to you some draft about this.
Okay. Very
Okay.
good.
I have one comment, Dr. Subject. When I looked through your paper, I had a comment right very near the beginning, and maybe if I just show you, it's not too serious a comment, but if I'd like to just share this screen just for a moment and just
Okay.
point at this. So can you see my
Yes,
screen?
I see
Yeah.
it. Yes.
Mhm.
Yeah. So in this first section, you immediately refer to this S plus N, but I don't like that. This comes immediately after your introduction and abstract, but we jump quickly to talking about this
Yeah, the simplest
space.
example.
Yeah, so I'm just a little uncertain to understand the notation. You know, like S plus N. You haven't previously introduced this notation, and so I was, when I started to read this, I was sort of struggling to say, well, what is, S superscript plus subscript N?
Well,
I
yeah,
don't.
yeah. S is a simplex defined by, well, first of all, we have the notion of a null vector. Okay, that's just the A's are null vectors.
Yeah,
A squared
okay,
is
we've seen those before, but we haven't seen the notion of simplex.
okay, yeah, but just
defined.
take two vectors, which don't, that they define it with the origin 0, A1 and A2, define a two-dimensional simplex. In fact, you can use barycentric coordinates then to name all the points of R2 in terms of those points then. Okay, so you pick two null vectors which have square 0 with respect, and those are null vectors from the origin, okay? And then you can name all points, well, in the simplex itself by barycentric coordinates. Now, yeah, I need to make more pictures of what we're talking
Yes,
about.
a picture at this point would be very useful. Um, I think you do have one graphic further down here.
Yeah,
where
okay,
you're-
there you have a picture.
Yeah. So for example, it would be
So you
good.
have one, that's right. So the vertices represent A1, A2, and A3. So we're in three-dimensional space. You see the wedge product of the A's, and you can think about those as being null vectors on the cone, the null cone in space-time. Okay, you have three null vectors, A1, A2, and A3. The wedge product of those things is not zero. They're linearly independent. Okay, so then you take V1 and V2 inside that, that's the simplex then defined by those A1, A2, and A3. That's a simplex. And you can represent any points in the simplex, connect the edges together,
So
A1
you
to
mean,
A2, and then you
so
can,
by simplex, you would mean the same thing as a subspace or something like this?
yeah, well, it's dividing R3 into different parts, okay? So you of course you can name any point within the light cone by a linear combination of those three null vectors. Okay, so the simplest case is what I'm referring to in the previous, which you had. Just take a face of that, A1 and A2. Then all points inside that can be named but with barycentric coordinates, V1 and V2.
And so whenever you're talking about S plus N,
Yeah, that's a simplex defined by
but do
those
you mean,
endpoints.
I guess I didn't quite appreciate what you meant by simplex. Like, if you substituted just subspace, maybe um, it's a subspace of a linear space of some sort. Um,
Yeah, well, I want to use those barocentric coordinates because that's important in the discussion. But that's the thing. I do need to make more figures to make it clearer what the ideas are. I'm sorry that I wanted to get something up before I left, coming down here. So that was the best I could do in the time I had.
Okay, well, that, I guess I could have also easily highlighted the word simplex here because I didn't sort of see the connection with what you were doing in the past.
Well, you can go down the line there. It says a position vector X in R2. Okay, then I'm trying to use that idea to, you're still in R2, or in the simplest case in R2 here. And you can name different you're partitioning with a cross. Well, basically think about it as light cone. The horizontal line, the vertical, the diagonal lines are in 2 dimensions to define the light cone in 2 dimensions. If you have, a null signature, 1, 1, for example, the geometric algebra 1, 1. You have a light cone in 2 dimensions. If you have my, yeah, well, anyway.
Well, okay. So my only comment then, I guess, is just that I would find it convenient in reading this to have
It is
a
sparse.
gentler introduction.
Yeah.
No?
Yeah, I should have more
Something-
pictures, but I just didn't
Yeah,
have
pictures
time.
or don't depend on my necessarily knowing what you mean by an n simplex in this context. Like
Yeah, you look up simplex in Google. It's basically, I'm not using any new idea there. The simplex is a simple, it's like a triangle defines a simplex. The interior points of a triangle can be named by positive coordinates with respect to the edges or with respect to the vertices of that sim. So a triangle is a 2 simplex. Well, then I'm only using the idea of you're naming those points on the simplex with null vector, the vertices by null vectors from the origin of some space, of higher dimensional space.
Well, okay, maybe there is some intersection here with what Jesus was talking about, because perhaps the concept of simplex itself is related to order to the order of the graph, right? So that here you're just labeling the vertices of the simplex, but you could also label the simplex itself, right?
Yeah.
As an
Yeah.
object, right?
Yeah, I think a very important concept that real numbers leaves out is that more basic than real numbers are these nilpotents. So what is a nilpotent? It's a number which is not equal to 0, but which have square 0. While we have numbers which are not equal to 0, which have square -1, we call those imaginary numbers. Then we have numbers which have square +1, which are not plus or -1, which are unit vectors, for example. So a nilpotent is like it's a vector, but it has square 0, but it's not the 0 vector. But they're still vectors. And in fact, of course, that defines Grossman algebras. You take n vectors, which all have square 0, and you wedge them together. You get an n vector then. So you can use null vectors to define dimension of a space. But that does not mean that interior points of an edge are not all null vectors, because the null vectors are correlated. The edges are correlated. The vertices are correlated. And that's where we had that idea of a duality I started out with. AB plus BA is equal to 1, but A squared and B squared are equal to 0. So I think that's very important concept that should come in with the definition of real numbers. So people extended the real number to the complex numbers. Well, that's great. But then you can also extend to unit or null vectors. And that really is what defines Grossman algebra, the null vectors. Now, relationships between two Grossman algebras, that's what defines matrices, everything else that comes afterwards. But that's what I call correlated null vectors.
Mhm. Okay, well, that's I hope we haven't lost the Dr. Sobczak again.
Okay.
Yes, seems to have.
Yes.
Well, I think it means that we should continue in 1 week, and that he'll have a more stable connection,
Yes.
and perhaps we can our discussions can be sort of focused at that time on this paper that he has drafted so far, and then oh yeah, okay, we'll see you connected again.
Okay, I'm back at least for a minute here.
Okay, so perhaps we should agree then that we would meet again in 1 week's time,
Okay, I think that's great. Good
and
idea.
then we would focus then on your presenting this material, right, to this.
Okay, no, that's fine.
That would be good, and that will give Jesus a bit of time to also collect his notes on higher order or multigraphs or multigraphs of multigraphs and that sort of thing, and
Okay.
if we can, maybe before the end of the year we can sort of conclude with some discussion of how they might be related to each other. That would be good.
Okay, sounds good.
Okay.
Okay.
Thank
All right.
I'll try to get better with this internet stuff here. But I'm just setting up again, really.
No problem.
Okay,
All right. So we'll see you both again in 2 weeks. I know, in 1 week. In 1
1
week
week.
time.
1 week.
1 week
One.
time.
Okay. See you.
Okay.
Very
Bye.
Bye
good.
for
Have
now
a good
then.
week.
You too.
Take care.
Mm.